Okay, welcome everyone. Welcome. My name's Larry Kramer. I'm the President and Vice Chancellor here at LSE, and it's my privilege and pleasure to welcome you all to this very special event hosted by the Department of Geography and Environment. Tonight's event highlights something that we don't actually focus on enough. And by we, I mean not just LSE or even the higher education sector, but really our society as a whole, which is the relationship between the physical and social sciences. Being at a social science institution, I don't actually get to introduce events like this all that often. An event about, the sort of cutting edge frontier of particle physics and astronomy and the pivotal role that major research infrastructure actually plays in advancing our understanding of the universe. And of course, that sort of work is more than just interesting and certainly more than just theoretical. Beyond just pushing the boundary, I said beyond just pushing the boundaries of knowledge, these groundbreaking scientific endeavors, which include everything from understanding the nature of dark matter to exploring the origins of the universe, actually have pretty significant consequences that make a huge difference in our everyday lives. The organization that tonight's speaker will soon lead, the European Organization for Nuclear Research, known more colloquially as CERN, is one of the world's most important and impactful scientific infrastructure organizations. It's also arguably one of the great diplomatic achievements of recent decades. It's a world-renowned intergovernmental organization comprised of member states who agree on almost nothing else, but somehow have managed to come together to make this institution really work. As our discussion tonight will make clear, the socio-economic impacts of big science are huge. Think, for instance, just of the flow of talent and investment within and between countries and regions that goes along with this kind of work, particularly now in the context of intense global competition for technological leadership. There may be no one better able to help us understand these impacts than tonight's speaker, Mark Thompson, who is the Director General Designate of CERN. Mark will formally take up his new role in January 2026. He was previously the Executive Chair of the Science and Technology Facilities Council in the United Kingdom, and he remains a Professor of Experimental Particle Physics at the University of Cambridge. Since completing his doctorate in particle physics at Oxford, Professor Thompson has been a research scientist at CERN, where he played a leading international role in advancing neutrino physics and research for future colliders. Professor Thompson is credited in more than 1,000 publications, as well as the author of a widely adopted textbook, Modern Particle Physics. As a national and international research leader, he served as the UK delegate to CERN's council, and he played a pivotal role in establishing the long-run UK research and innovation infrastructure roadmap and investment portfolio. In addition, we have two outstanding discussants who will reflect on Mark's presentation. Sarah Sharples is Chief Scientific Advisor for the Department for Transport, as well as Professor of Human Factors in the Faculty of Engineering at the University of Nottingham. She has led research in transport, manufacturing, and healthcare focused on understanding how to design complex systems that enable both people and technologies to reach their highest potential. She was president of the Chartered Institute of Ergonomics and Human Factors from 2015 to 2016 and was elected to the Royal Academy of Engineering in 2024. Also joining us, Riccardo Crescenzi is a professor of economic geography at LSE and deputy head of Department for Research. A leading scholar in the economics and geography of innovation, he's the LSE principal investigator for a major Horizon Europe and UK research and innovation project on inequalities in the era of global megatrends. Riccardo's work focuses on innovation, new technologies, foreign investment, global value chains, and public policy analysis. So tonight's event is part of an ongoing collaboration between LSE and CERN that is led by Professor Crescenzi. The collaboration began in 2020 with an initial 4-year research grant to study the territorial impacts of CERN procurement as part of a broader investigation into CERN's territorial impacts. The collaboration has now grown into a doctoral training partnership collaborative, and it was recently awarded a UKRI Metascience grant for a project entitled Big Science Beyond Science, the Innovation Impact of Research Infrastructure Procurement. Dr. Thompson's lecture is an opportunity to both celebrate and strengthen the ties between CERN and LSE, as well as to foster further collaboration on the economic impacts of science and technology, and to showcase LSE's research in this domain. We have a new master's program in innovation policy that will launch next September, and it will explore many of the themes that we'll be discussing here tonight. After the talks, there'll be a chance for you to put questions to our speakers. I will try to ensure a range of questions from both our online audience and our audience here in the theater. And with that, it is now my pleasure to invite our keynote speaker, Mark Thompson.
Well, thank you for that introduction. It's unusual for me to be at a department like this as a very hardcore physical scientist, but it's a real pleasure to be here. And I think the introduction actually made it very clear that the interaction between the social sciences and the physical sciences are becoming increasingly important as we really have to evidence why the investments in big science are so important. Very much looking forward to the discussion. So my presentation is going to touch on science, of course. That's the bit I like. There won't be a single equation. I just promise you that. But just give you some sense of what we actually do at CERN. And then I will introduce, in rather broad terms, some of the benefits, the wider economic benefits. And that will hopefully then feed into the discussion afterwards. So change the title a bit, Big Science and Why It Matters. Perhaps why I think I've got a kind of almost unique position to be able to discuss this. I've had many roles. So I've been a researcher, I've been an academic, I've led research projects, big research projects, both in Europe and in the US. And before my current role, I was executive chair of STFC, one of UKRI's councils. So that gives you the perspective, not just from the academic side or from the leadership side, but also from the government side. And these questions about value for money, why invest in big science, come up, and I think we can defend them. I think we have defended them very, very, very strongly. Anyway, pleasure to be here. Really looking forward to the discussion. This is what it's all about, though. Ultimately, what motivates me and motivates most of my colleagues is we want to understand the secrets of the universe. It's a really exciting mission, and I'll come back to that excitement bit right at the end. This is what we do. What we're trying to do is understand the universe from the Big Bang, right from the beginning, to what we see today, the galaxies, the stars. And we can do that in two ways, both big science, telescopes. So in telescopes, we look backwards, going from right to left. And you can basically look back in time throughout the universe and see what matter is out there. But you can only do that up to a point. There is this point, 380,000 years after the Big Bang, where you can't see any further. There's just everything's too dense, the light does not get out. So if you want to see what happens before then, you have to try and recreate the conditions, not at the Big Bang, but close. And that's what we do with our particle accelerators. We're trying to put a lot of energy into particles to make the conditions a bit like existed shortly after the Big Bang. You actually might notice another period, a historical period between that bit there, the sheet, the plane of blast scattering, and when the stars start lighting up. That's called the cosmic dark ages. That's a really boring bit of the universe. The universe is just full of hydrogen, gradually clumping together before the stars ignite. But the next generation of big radio telescopes is going to look into that period as well and understand what happens during the dark ages. So that's what we want to do. What we're trying to do in particle physics, we're trying to answer some very big questions. So what's the universe made of? What are the building blocks, the particles? How does the universe work? So what are the forces between the particles? How does that work? Ultimately, we would like to include gravity in our model. So gravity is the thing we're all experiencing, but actually we don't really understand gravity at a very deep level. And ultimately, then we want to figure out how the galaxies, stars, black holes evolved. This thing that's out there, we know it's there, called dark matter. It's only 95% of all of the matter in the universe, or dark matter and dark energy. We don't know what it is. I mean, so we know a lot, as you'll see, but we don't know everything. So that's our mission, is really to try and understand the universe from the start to what we see today. This is just a slightly basic introduction to particles, just to give you some sense, because I know it's a very mixed audience. These are the building blocks of what I would call the low-energy universe. The low-energy universe is what we are in today. It's not what we do at our colliders. That's the very high-energy universe. So take some matter. That's a block of copper. That's, as you know, made up of atoms. So we're delving down one layer deeper. Atoms are made up of a fundamental particle, the electron. That's the thing that orbits the nucleus, so there's a bit in the middle. And it's basically the number of electrons, the nature of the electrons, that determines chemistry. So the electrons in the atom, that really is chemistry. If you delve deeper, there's a nucleus, that blobby thing there. That's made up of protons and neutrons. They stick together very, very tightly. They're not fundamental particles now. We thought they were, but we now know that actually they're made up of other particles called quarks. So a proton contains 3 quarks. And going deeper, we think quarks are fundamental particles. And the reason we kind of think they're fundamental, at least at the moment, is we can't measure their size. We've tried, and we know they're smaller than a very, very, very small number. So that's basically it. That's what everyone around here, we're made of basically electrons and quarks, an up quark and a down quark, and some combinations. And there are particles called neutrinos whizzing through us, passing through us all of the time. That's 4 particles. That's a very, very basic, very simple picture for the low-energy universe, the universe we're in now. Now, of course, reality is a bit more complex than that, and I'll show you what that means in a minute, but actually not much. So the universe, at least at low energies, seems to be quite simple, quite remarkable, really. We don't just want to know what the universe is made up of. We want to know why it is the way it is. So that's a really deep, more profound question. So that's our mission, to try and understand what the universe is. And that's really what CERN does. I've got a couple of slides just to introduce CERN, because again, it's probably not familiar to everybody. This is big science. This is one of the detectors at CERN that images the particle interactions. And you can see at the bottom there's a person just for scale. And of course, this is foreshortened as well. So actually, that doesn't do the scale of this experiment. This is a physics experiment, real justice. These are very, very large research infrastructures, very large investments to do this incredibly complex science. So CERN is the world's biggest laboratory for particle physics. Undoubtedly, it is at the forefront of science. There is no place like CERN elsewhere in the world. It's an amazing place, amazing engineering. We try and do physics, but it is an engineering laboratory primarily. Most of the staff at CERN are engineers and technical specialists, and it's then the scientists from around the world that come and do the science on these facilities. It's big. You can see this diagram here. The CERN site is actually, the main CERN site is there. To give you a sense of scale, the radius of that small ring there is 1 kilometre. Exactly 1 kilometre, actually. So it gives you a sense of scale. And this big ring out here, the very large thing that straddles the border, that's the Large Hadron Collider. It's underground. It's just to show you where it is. CERN's mission is a beautiful mission, basically understand at a very fundamental level the laws of particles in the universe. The other thing that I think is really important, and I will touch on this later, CERN is an amazing place, and it's amazing because it's built on just over 70 years now of deep international collaboration. Stable collaboration between European partners, collaborating together on a fundamental physics. So it's not a political area, this is fundamentals, common scientific goals. And that's really, I think, why CERN has worked so amazingly. Just to give you some numbers and some sense of scale. So CERN was founded 70 years ago, initially with 12 European member states, one of them being the UK founding member. There are now 24. We have a few associate member states, 10, and some observers who still put money into CERN. Budget is about £1 billion a year. Again, to put that in context, that's the equivalent budget for a medium-sized European university. So it's a big budget, but in the grand context, it's of that scale. And to give you the sense of the other scale, there are about 2,500 staff there, 1,000 graduates, And the key, the thing that really makes this work, 12,000 users. These are the scientists from around Europe and around the globe that come to use CERN to do their science. So hopefully that gives you a sense of scale, roughly 3,500 employees if you include graduates, and then 12,000 plus users. So it's a big, big endeavour. So what we do at CERN is try and probe and understand the universe. And to do that, we are constantly pushing the boundaries of engineering and technology. And I'll say this a few times in this lecture. The question we ask ourselves is often, we would like to understand X, dark matter. How do we do that? Well, we don't have that technology, so we can't do it. So we have to find the technology. So scientific mission pushes the technological goals, and then we work really, really hard to develop the technology we need to do the science. So this is a very interesting way around, and I'll come back to that at the end. So we're constantly pushing the boundaries of technology to do the science that we know how to take the next step. Central technologies, I would say there are three main areas of technology at CERN. Actually, I don't really think this does it justice. Obviously, we build big particle accelerators. That's one of the smaller ones, in fact. We've got to take our particles, give them a lot of energy before we smash them together. Detectors, I'll talk about what a detector is. That's, sorry, that's not a very obvious description. These are our experiments, but these experiments are massive. And shouldn't neglect computing. What we produce out of these big detectors is vast, vast amounts of data. And CERN has been at the cutting edge of big computing for many years, distributing it around the world before there were things like clouds, public or private clouds. So computing is a big part of CERN's mission. Right, now for the fun bit, I get to talk about the Large Hadron Collider, which is an absolutely amazing machine. The Large Hadron Collider is our most powerful tool, globally our most powerful tool to do this science. It's large, 27-kilometre circumference ring, as I say, straddling the French-Swiss border. The Hadron, it accelerates hadrons. Well, actually, it accelerates protons, but protons are a type of hadrons. It can also accelerate ions as well, but quite fast, 99.9999991% of the speed of light. I hope I got that right. Probably didn't, actually. And of course, ultimately, what we do is we send beams of protons one way around the ring and another set of beams of protons another way around the ring, and then we bring them together, smash them together as hard as we can. So we put as much energy in those protons, use Einstein's E equals mc squared, so as more energy we can put in those particles, the more mass of something new we can make. So that's really what we're trying to do, get back close to the conditions like at the Big Bang. And then we photograph those collisions, and I'll try and show you how we photograph those collisions. I just want to emphasize, this is incredible. This machine, it never ceases. The more I learn about the Large Hadron Collider and what makes it work, the more I'm amazed. Just controlling the current on the magnets, the level of precision you have to do that to not lose the beam, is unparalleled. So you have to go out to all of the best measurement institutes, develop new technologies to keep your current stable to 1 part in a billion. Very, very hard to do when it's hundreds of thousands or tens of thousands of amps. We accelerate the protons around this ring, and then, as I say, we smash those protons together 40 million times a second, so that's quite a lot. And the thing that I think is really somewhat scary about this machine, it's got 350 megajoules of energy circulating both ways around the machine at any one time. That is the equivalent to the kinetic energy of 1,000 stampeding African elephants. I believe this is true. And they are African elephants, not Indian elephants. That's a lot of energy. Or 777 as it lands. That's a lot of energy. And that's one of the real challenges about the LHC. If you lose that energy in an uncontrollable way, you can melt tons and tons of copper. So you can basically destroy that machine instantly. So that engineering control is absolutely critical to the machine. The way it works is we then have, so this is a bit of a diagram. So we have about 2,500 bunches of protons. They come in little clumps, one going clockwise, one going counterclockwise. And then we bring those bunches of protons together at 4 places around the ring. These are our big experiments. CMS at the top, the ATLAS experiment at the bottom, that's very near the CERN site. These are, if you like, multi-purpose detectors to try and do multiple types of science. So these aren't experiments like you would be used to in a physics lab or in a university where you design a small experiment, it does one thing. What these experiments do, they take lots of data, they record lots of images, and then the scientists, the graduate students, will sift through that vast amount of data and try and understand the science in that vast amount of data. So there's only one set of data, and we just want lots and lots of data, but many people do different things with that data. Then we have 2 more specialized detectors called ALICE and LHCb that are designed to do, in the case of LHCb, look at the difference between matter and antimatter. And the case of ALICE, it's trying to create a different phase of the universe where quarks and other particles were deconfined and interacting with each other. So that's what we do. The picture, I just like showing these pictures, actually. I should, just again, these are very, very large, very, very complex instruments. The thing I want to emphasize here, how do you build one of these? You can't go to industry, because you might be able to go to industry to get some of the pieces, but you can't go and say, I would like to buy an ATLAS detector. The thing that's really remarkable about this, these detectors are built primarily by colleagues in universities, in university departments. In the case of ATLAS, 3,500, 4,000 scientists collaborating. Oh, my screen here is gone, that's back. And actually building bits of this and then integrating it all together. So it's this incredible collaborative effort in a very unusual way of operating. So it's really interesting. And of course, some of the technologies you have to procure from industry, but you don't buy the whole detector from industry. So it's a very different way of working. In essence, these are giant cameras. So you can see that, can you see this bit? They're cylindrical in geometry. So what happens is the protons will come in, one side, another side, smash together, create lots of energy. Einstein says E equals mc squared. You make a big massive particle. It will decay in a tiny fraction of a second. And then what you see is you see all of the bits that come off, the spray of particles that come off, and you image those in these cameras. They're kind of like cameras. This picture here, to the trained eye, this is possibly a Higgs boson being produced here and then decaying into 2 particles of light, photons. So you can actually look at these images by eye and get a reasonable sense of what actually happened at a really fundamental level. So let's just dig a bit deeper into the detectors. They are incredible. I think they are the most complex detector systems ever built. Here's the cartoon again. You've got 2 rings of protons. There are actually 2. You don't want them colliding in the middle. You want them to collide where you want them to. They're 25 nanoseconds apart, these bunches. That's the 40 million times a second. They smash together. Every time you get a bunch smashing together, remember 40 million times a second, you get about 1 billion interactions. So 1 billion protons will interact, proton-proton collisions. And the real challenge there, you have this spray of particles coming out, and really the most interesting events are very, very rare, where you produce a Higgs boson or where you produce something different. So you are looking at 1 in whatever that very large number is. But that just gives you the sense. So you're now sifting through this vast amount of data to try and pick out the bits that are telling you something about fundamental science. And that's basically what these detectors are doing. Just to try and emphasize again, I think it's an important point. This is just a similar picture that I showed before. Protons come in. They actually come in these tubes. This is where the beam is contained. Smash in the center of the detector. Look at the energies and the directions of all of the particles that come out. And that enables you to figure out what actually happened in the interaction. So they are like big 3-dimensional cameras taking 40 million pictures a second. And then out of these 40 million, you select about 1,000 and you throw the rest away very, very quickly. And then you process those and understand those later. So that's the detectors. A few words about the Higgs boson and why it's so important. So CERN has actually made several Nobel Prize winning discoveries. I won't dwell on these. W and Z back in the 1980s. The big one recently, and this is a massive, massive discovery, the Higgs boson discovery. This is not an incremental discovery. This is a giant leap forward. That was discovered back in 2012. So why is it so important? So first, when the scientific community was talking about the LHC, the prime scientific motivation, not the only motivation, was the Higgs boson. It's not another particle. You shouldn't think of this as, oh, there's another particle. Oh, they found another particle. Absolutely not. It's something completely different. So now I can go back to the picture I had before, where I said there were 4 basic particles, 2 quarks, the electron that circles the nucleus, and these strange things called neutrinos. We actually know that there are 2 copies of each of these fundamental particles. We think that's all. We don't know why. We don't know why there are 2 copies. So that gives you 12 matter particles. So the electron, a heavier version of the electron, and an even heavier version of the electron. And we have particles that mediate the forces, create the forces between them. Now, this is a very strange thing. The universe is actually a very strange place. As far as we know, these particles have no size. So we're made out of stuff that has no size, pinpricks in space-time. And without some magic, that's called the Higgs, this whole model of particle physics only works for particles that don't have any mass. So you kind of really, the model we have says no mass, no size for particles. It's quite strange. The Higgs is the thing that makes it all work. It's unique. It's what we call a scalar field. Doesn't really matter what that means. But its presence gives all of the other particles their mass. So if the Higgs wasn't there, all of your electrons would be massless. They'd all be disappearing into the universe right now at the speed of light. So that just gives you a sense of how important the Higgs boson is to really understanding our universe. This is, I try to give a very dubious analogy that my colleagues in particle physics don't like, but I do. So you can think of the Higgs, let's call it the Higgs field, as a property of the vacuum. So you go somewhere out into the deepest parts of the depths of the universe, the Higgs field is always there. That's very, very, very unusual. For other particles, that's not the case. We have a name for it, calling around expectation values, vacuum expectation values. In some sense, the Higgs field is always there. So what the Higgs field does, so this is my picture of this is my very dubious analogy. It makes the vacuum sticky. It makes nothing in the universe is kind of sticky. So if you're a particle and you want to move through that sticky field, it feels like you've got a lot of inertia. It's very hard to accelerate. So that's the example that happens regularly in, I'm not sure where this is. I always say it's in Gloucestershire, but I'm not sure it is. But you can imagine yourself walking through this field of sticky mud. It's very hard to walk or crawl. And in some sense, that's how the Higgs field gives particles their inertia, their mass. We have a technical term for it. It generates something that looks exactly like mass, but it's not really. Now, what we then do at the LHC is we're actually taking the Higgs field and we're smashing it really hard. So we're now hitting that Higgs field when we collide our protons. And the ripples in that Higgs field, those are the Higgs bosons we see at the LHC. That's a terrible analogy. It's not a terrible analogy. I like it. So what next? Very quickly. Firstly, we know a huge amount about the nature of the universe. The progress we've made over the last, let's go back 120 years, absolutely enormous. From almost not really understanding how the universe fitted together at all, to understanding, getting to the point where we can start to think about going from the Big Bang to where we are today. But there are gaps. And here are some gaps. Well, we don't know what the dark matter is. It's only 95% of the universe. We don't know whether the Higgs has anything to do with the dark matter. Does it see the dark matter? We don't know if the Higgs is a fundamental particle. We know the universe is made of matter. Where did all the antimatter go? We actually don't know. Gravity is a very, very, very weak force. Might not feel like it today, but that's because there's a lot of particles and it all acts on all of them. And finally, I talked about those 12 particles. They all have different masses. We've got no idea why. We don't know why there are 12. We don't know why they have different masses. We don't know what their masses are, why they have the masses they are. So at least 3 of those questions probably have something to do with the Higgs boson. And anytime I write down my favorite 6, this is 6 questions, I gave a talk earlier this year, I wrote down 10 questions, half of them have something to do with the Higgs boson. So these are really, really important. Very briefly, what next? And then I'll talk about the economic perspectives. Next, we know what we're doing next. We're building what we're calling the high luminosity LHC. It's like taking the LHC, keeping most of those nice blue magnets you saw in the picture, but right by the experiments, putting some new red and yellow magnets in their place. These are really brand new, cutting-edge technology that did not exist when the LHC was built. Put it simply, what it does is it will make the LHC brighter, 10 times brighter. So you can think of that. We take the same time period of data again, but we're going to get 10 times the amount of data we have now. So we're right at the start. The detectors are being made better, so we're making our cameras more powerful. And what we're seeing, our brilliant young researchers now being aided by AI tools. That's not ChatGPT, by the way. These are AI techniques that allow you to get more out of the data. That is giving a lot more power. So effectively, this is a massive scientific opportunity. It will run from 2030 until 2041. Basically, a lot more data, better detectors, new techniques, and hopefully, well, definitely real discovery potential, and hopefully discovery. That's 2040. These big infrastructures take a little while to build, so we're now thinking about what happens after, what happens in the late 2040s. We have a vision. It's a really exciting vision. The Higgs boson is so important, it's so new, completely different from anything else. We want to really study it, understand what it is. I didn't really emphasize enough, it's very strange. It's a very strange type of particle. It just doesn't feel, it's nothing like any of the others. It doesn't feel quite right, so really interesting. So we're planning to build a new Higgs factory machine. This comes with a very imaginative name, the Future Circular Collider. It will get a better name at some stage, I hope. This is a 91-kilometre ring. So you can kind of see the Large Hadron Collider there. The Future Circular Collider is about 3 times the size. Again, straddling France and Switzerland, and this time going underneath Lake Geneva. Very ambitious, very exciting scientific program. It's Higgs boson, but much, much, much more than that. We're targeting start of this running in 2045, 2048, that kind of timescale. But for that to happen, we have to take a decision on this in the next few years. The total cost, which I think is relevant to the discussion that comes later, it's about 15 billion Swiss francs, depending exactly what you include in that, over 15 years, shared between 24 member states of CERN with contributions from other major economies. So the number is large, but it's shared, it's over a long period of time, and there is only one CERN globally. Maybe come back to that later. Incredibly exciting. This is not yet approved. We go to our member states. We ask the member states. They have the money. But we're hoping for a positive decision in a few years' time. Right. Now just trying to say, I'm trying to give a few words about my sense of the broader impact, and that will open up the discussion and enable the real experts to give their views. Firstly, science. CERN has made incredible scientific contributions. That's CERN's raison d'etre. But actually, personally, I believe, even though I'm a particle physicist, it's not just the scientific bit. There is a cultural aspect here. Humanity discovering the universe that we live in. I think that resonates, hopefully resonates with everyone. So I think there is a deep cultural value in what we're doing here. The whole piece around collaboration, science diplomacy, whatever you want to call it, CERN is only what it is, and I say it's really fantastic, is because of this 70 years of deep international collaboration across Europe. Countries can come together behind a common positive goal, something that is often needed at the moment, I'd say, and they do. But there are other direct economic benefits. I'm just going to touch on these and just give my very personal view on what these are. Firstly, I don't think this is easily quantified, and that's why we very much welcome the study and the meta-science program that we're going to hear about shortly. It's very difficult, though, I think, to quote a reliable measure of return on investment. How much, if you put £1 into this, how much do you get out? That's not why we're doing it. We're doing it for the fantastic science. Technology development, and I'll try and illustrate this, is often very hard to say, well, what if we didn't have a CERN? What wouldn't we have had? And how do you then kind of look at the economic impact of that? And timescales are very long sometimes. Here's a nice example. This is just a 100-year example. So when Einstein wrote his general theory of relativity, published 110 years ago, it was kind of fairly clear there was no practical benefit. It's very, very fine. You know, this is of no relevance. This now underpins GPS. So if you didn't understand general relativity, we would not have accurate GPS. So that's the kind of science where fundamental science can take a very long time to mature. Just a few numbers. So this was a big science. This was a study and a report on the benefits to the UK of membership of CERN. Just to give you some sense of numbers, this is a 10-year period, 20,000 papers published. Now, whether you call that a benefit, economic benefit or not, that's a question. Amongst those papers, the Higgs boson discovery paper, that was one of the most highly cited papers in any subject. Training, just to give you some sense, in that period, 10 years, about 1,500 UK scientists and engineers were trained at CERN. Now, most of them don't stay at CERN. Most of them don't stay in particle physics. They go into industry. They go into other research sectors. There's a piece that I don't think we can kind of underestimate, and that's inspiration. Subjects, I think, like particle physics and astronomy are inspiring. I mean, they're very tangible. I mean, if I want to understand what's out there in space, that's astronomy. If I want to understand how the universe works, that's particle physics. I think that's very inspired me. But I think they do have the power to inspire young people, not necessarily to do particle physics, but go into technical subjects. CERN has a very, very strong engagement program. So from the UK, we get about 500 school groups visiting CERN every year, just to give you some sense. And of course, when CERN spends its money, a lot of the money is actually spent in industry. And again, this just gives you some sense that this was a 10-year period. About 500 UK companies were awarded high-tech contracts, revenue about 200 million. But there's a multiplying factor there, because it's not just buying something. You're buying something, but it's high-tech, and CERN will then help transfer that technology to the companies. Not always, but in many cases. So just a couple more slides. So I think this is a personal perspective. So I think one of the largest impacts of big fundamental science projects is that pushing the technology beyond the current state of art in a way that's driven by science. And I think sometimes can be a misperception that science happens kind of incrementally. You sit there with a blackboard, you think about what do I do next. It doesn't really. It really progresses when you have a major technology capability change. That's the thing that makes the biggest difference in science. So that's what we do in particle physics. We try to do the near impossible. We try not to do the impossible. That's never a good idea, but get as close as possible to get a better understanding of the universe. This requires a new capability, a giant step forward in precision or something like that. And then, as I said previously, we try and develop that technology. And then that technology or capability might have wider applications. So this is an innovation cycle, but a very, very different one. This is driven primarily by the scientific need. You're not trying to innovate for innovation's sake. You're trying to answer some really, really difficult questions, which will need some really, really clever technology. I'll skip that slide. CERN was the birthplace of the World Wide Web. We all know that. But I've got two more slides. So this is, again, where I think it gets difficult to actually quantify the benefit. And these are really the big disruptive changes. So the World Wide Web was kind of born at CERN. It was there to help share information and data between the particle physics community. So science-driven mission. Would it have happened without CERN? Something would have happened. It would have been developed in some form, but it might not have been in a very open access form. It might have been completely proprietary. So I think there are clear benefits that the development of the World Wide Web at CERN, and CERN has a very, very strong open science culture, was open. So accelerators, this is technology that developed as our main tools for particle physics. If we didn't have accelerators, we would not have the most advanced, most sophisticated cancer treatment. This is called Hadron therapy, ion therapy. We can produce medical isotopes, really, really important. But taking another leap forward, this picture at the bottom is the diamond light source in Oxfordshire. We wouldn't have this. This is basically inside this ring, it's a 500-meter ring. There is an accelerator there. Actually, there's an accelerator and a storage ring. That technology came out of the technology developed in particle physics. If we didn't have the diamond light source, we wouldn't understand very much about structural biology. This drives drug discovery, advanced materials, much, much more. So this is the really deep, as I say, disruptive technologies and the long-term impact they have. So I say the reason we have this technology is we wanted to do fundamental science. And then, of course, I think it is arguable that without that mission, we would not have these big accelerators today. Finally, I like this one as my final slide. I think it's a very nice example. When the team at Atlas were developing that big detector, big Atlas detector, looking at the silicon sensors to make up part of their big camera, it's a very, very high radiation environment. So traditional silicon does not survive. It would die very rapidly. So that required designing special radiation-hard technology. So it's like having a radiation-hard mobile phone camera. Sounds very niche. It sounds incredibly niche. But a few years later, this new technology enabled discovery. So Richard Henderson won the 2017 Nobel Prize for Chemistry for developing something called cryo-electron microscopy. So this allows you to take soft biological samples, freeze them, and actually see these biological molecules almost mid-movement. The reason this was possible was that we had this new radiation-hard detectors, these silicon sensors, that you could fire high-energy electrons at, and they would survive. And that really kind of meant that this field could develop in the way it has. Cryo-electron microscopy is revolutionizing our understanding of structural biology, made possible by a new technology that came out, not directly, that wasn't what we were trying to do, from particle physics. And this is where I think the real challenge is to really quantify what is that impact, particularly if some of these impacts are 20, 30, 40 years downstream. Anyway, I think that's a nice example. Final words. Hopefully I've given you a bit of a sense of what we try to do at CERN. We are trying to address profound questions. The other thing I wanted to try and do was convey the scale of what we do at CERN. I mean, this is big science. This is big, big, big science, as you can see, both the experiments and the machine. Really want to emphasize the remarkable engineering here. CERN is an engineering laboratory that is used by the scientific community, the physicists, to do their science. Deep long-term international collaboration, maybe we'll touch on that. And finally, I think just the benefits beyond science of forefront research. We are developing technology. We are constantly pushing the boundaries. The technologies we're looking for at the moment are in high-temperature superconductors, very, very high field magnets. We will need those for our next colliders. We don't know what applications they will have, but we are pushing on that technological directiveness. So this technology then can drive innovation, competitiveness, and ultimately, hopefully, growth in high-tech sectors. And on that note, I will thank you and stop.
So, I do have to say, I studied history and law and political science. I love that. Social sciences, I think, are incredibly important. None of this stuff, et cetera, but it isn't possible not to be awed by the. I visited the Stanford SLAC, and it's right. The little kid in you is just like, this stuff is so amazing. I just had to say that. So we have the two commentators to reflect on some of what you just heard, and so let's start with you, sir.
Thank you. First of all, thank you, Mark. I'm a Chief Scientific Advisor for the Department for Transport, and I find myself in all sorts of situations. And I was sitting here thinking, wow, I've got the opportunity to learn about all of the activities at CERN from the person in charge of CERN. So I really, really appreciate the whistle-stop tour through the amazing science that's being done. And then I was also sitting here and thinking, well, I was chatting to one of our ministers today, and if I bumped into him tomorrow and I said, oh, I went to a talk about big science and the Large Hadron Collider, I'm not sure he would see the relevance of that work and then some of the critical challenges that we're delivering within the Department for Transport and across government. You presented some really great questions that are at the forefront of your mind as a particle physicist and a leader of CERN, and I thought, right, okay, if I was talking to my fellow chief scientific advisors across the government departments, which I do very, very often, what questions are at the forefront of their mind? And I thought I'd just read some out. How do we deliver cleaner, greener, safer transport? How do we develop new approaches to clean energy? How do we maintain food security? How do we improve the lives of those in deprived communities? How do we manage and prevent chronic health conditions? And how do we tackle and prevent knife crime? Those feel like very different types of questions to the questions that you proposed, Mark. But actually, I think that conversations like this help us to make the connections between that fundamental theoretical discovery that comes through facilities like CERN and the practical realities of everyday life. Let me take that final example, tackling and preventing knife crime. How many of you have travelled through an airport? Okay, so when you go through an airport, you have to put your bags and yourself through detectors. Those detectors look at what you're carrying, they look at what's in your bags. Those use the types of technologies that are only possible because of initiatives like CERN, like magnetic resonance imaging, like detection of different chemical compounds that comes through many of our scientific facilities. Like facilities that require very, very large sets of computation to be conducted to enable us to have artificial intelligence models that enable us to detect materials as we pass through airport security. I think one of the most important roles of the chief scientific advisors actually is making the connections between some of the fundamental science that happens in universities and industry research labs all over the world and the practical problems that we have to tackle today. So, as Chief Scientific Advisor, I also work with my colleagues to advise government on strategies and policies around science. So the question we were asked today is why should we fund big science? You heard about the astonishing budget that's required to maintain a facility of the scale of CERN. And actually, I was surprised by how cheap it was. I thought it would be even more expensive. But we can't have a CERN in every county in the UK. How do we make sure that we've got the right facilities, not just for now, but also for the future challenges that we need to be tackling if we're going to address those challenges like clean energy, safer transport, food security? Well, I think one of the things that's most important is understanding that whilst the pretty pictures are of physical facilities, actually the physical facilities often act as a magnet for everything that happens around these facilities. You mentioned the importance of the people. We know, for example, at the Harwell ecosystem that you mentioned with the Diamond Light Source, there are 7,000 innovators, 220 organisations, and they're doing work on problems that are being tackled in everything from space, health, energy and quantum technologies that will transform the way that we can sense and perform computing tasks in the future. Having visited some of these types of facilities, you genuinely get a buzz because you realise that what these facilities do is they bring together physical scientists, engineers, and social and economic scientists as well, to all be thinking about some of the deep questions that the outcomes of the experiments that happen through these facilities really provoke, but also thinking about the practical applications of the science and the discovery that evolves. So for me, actually, the most important thing about these facilities is the people. But there are other things that come through as well. I mentioned the disciplines that people come from. Multidisciplinary collaboration sounds lovely in theory, is extraordinarily difficult in practice. You heard that I've recently been elected as a Fellow of the Royal Academy of Engineering. My first degree is in psychology, and I'm one of a very few number of people who have made that transition from fundamental social science into practical engineering. It's a really hard career to execute. And so thinking about how we help people have those genuine multidisciplinary teams, I think, is really important. The third thing that I think is really important is how we choose what to invest in. I sit here in awe and think, I couldn't have come up with the idea for CERN. I couldn't have come up with that idea. How do we make sure we're nurturing the brilliant ideas to come up with these types of experimental facilities in the future? But the real critical challenge is, how do we choose what next? And I think my question to you, Mark, that hopefully we can pick up on later is, what else do we need alongside the CERN facilities to help us make the discoveries that will propel us to solutions around engineering, biology and food security that we need in the future? The final thing I really want to sort of highlight, though, is that something I think we sometimes forget is the importance of public engagement with science. I actually first learned most about CERN when I was on a flight, and I picked up a documentary about the Large Hadron Collider and its construction, and it was brilliant. And that was a really great example of public engagement with science. I do worry that lots of these facilities feel anonymous to their communities around them, yet they are massive, massive pieces of our puzzle in terms of creating jobs and employment in all parts of the UK. So I think a challenge to us as well is, how do we make this accessible to the public, to decision makers, to industry in a way that's really, really meaningful? So the final thing I'll just sort of conclude with is what do I take away from this discussion? I already knew there was brilliant science happening at CERN, but I've realised, I think, the potential for so much more discovery. I think we need to think about what government can do beyond funding facilities, because these facilities cost and there is not infinite amount of money to fund these sorts of things. How can we make sure that we've got the right regulation to mean that when we come up with invention and discovery stimulated by the brilliant work at places like CERN, that we can actually pull it through and use it to make a real difference in our economy and our society? And how can we make sure that we're getting the right evidence about what science and engineering is doing that's really making a difference? And I know that my colleagues here will now provide us with lots of information about really understanding the value of science and discovery to the UK economy and society. So I really look forward to the rest of the conversation. Thank you.
Thank you.
Thank you. I mean, when you only have a fraction of the publications of the people sitting next to you, then you need a few slides. So I will. Sorry. So I will try to briefly discuss what Mark has mentioned in his absolutely enlightening talk along three lines. The first point that I would like to make is about the link between big science and innovation, where we understand innovation as the application to the economy of the technologies and the ideas and the discoveries that Mark has mentioned in his talk. So the link between big science and innovation, something on how we can track and measure the economic impacts of big science, and then finally something on the science of science funding. So let me start with one chart. There are only a few, I promise, but I think this is very, very interesting because shows us the value of patents. When we have a patent, is a way to protect an invention, to protect a new idea, but we also use them as a measure of innovation. How and to what extent we have new ideas that are applicable to the economy. And here, we are looking at through a rather sophisticated procedure at the economic value, the dollar value of patents. And what we have here is their distance to science. So how far away a patent is from science, from the science that Mark has discussed in his presentation. So here we can see, number one, when a particular patent, when a particular invention, thank you so much, is very close to science, meaning that the patent is directly citing an academic publication. And we see that a patent and an invention that is directly linked to science is a lot more valuable than an invention that doesn't. It's compared with a distance of 4 degrees, okay? And we can see that, so and don't do what our president suggested as a lawyer perspective, just add more citations to publications to increase the value of your patent, okay? That's not how it works. But if you measure, like if you look at actual patents and you want to see how far away they are from science, the closer they are to the science, the higher their economic value. So that's the first point. We can measure, in some sense, how and to what extent science can influence the economic value, the dollar value of new discoveries that are applicable to the economy. However, rather interestingly, if we look at how and to what extent the industry, the private sector, is investing in new science, we see that across different firms, looking at US firms, we see that firms are publishing less and less over time. So there seem to be economic returns to investment in science. However, if we look at how and to what extent the private sector is investing in science, we see that they are doing less and less of this. So that's an additional important stylized fact, because when we discussed about the cost of building something like CERN, we need to think about the private sector shying away from this type of investment. An additional important stylized fact is how difficult it is to come up with new ideas. So if we look at how new ideas are generated, we do see that new ideas are generated more and more through a collaborative process. Here we are looking at patents filed in the UK. And we see that if in the 1980s, between 20 and 40% of the patents were authored by one single inventor, today the norm across virtually all scientific fields is to have multi-patent inventors, multiple inventors working on the same idea. This shows that we need more and more people, more and more like different competencies, the interdisciplinarity, if you want, to achieve like new ideas. So this is like how research infrastructures step in. They bring in the resources, the capital, the funding that is needed for scientific discovery. They bring in the people. That is what Mark was mentioning before and Sarah was highlighting. They bring the collaboration that is needed for the advancement of science. So science, like more and more, needs this costly, sophisticated equipment, the capital, and need the collaboration. And these big science projects like deliver in part these capital, these ideas, and bring these people together. And that's why Mario Draghi, when in 2024 presented a big report on the competitiveness of the European Union, presented like large research infrastructure as a very important tool to achieve this coordination at EU level. These are very, very big endeavors, and they need coordination. So one thing, we cannot have one CERN in each county, but we cannot have one CERN in each country. We really need like a huge coordination of efforts and funding to be able to deliver the science that is needed to feed into our economies and generate economic value. And competitiveness, this is the objective of what Draghi was trying to highlight. The lack of coordination leads to duplications, and so we need also to reach a sufficient scale to be able to bargain vis-a-vis contractors that need to provide the different bits and pieces that form these incredible machines that Mark has discussed in his presentation. So how can we measure, like more concretely, the economic impacts of this large research infrastructure? And like Mark has given some examples. I mean, you can have some big inventions like the World Wide Web, or you have new ways to cure cancer like the proton therapy. And there are, however, a multiplicity of pathways that go from large research infrastructure into like economic impacts, like scientific production. We have environmental benefits, data and ICT that Mark has mentioned, training. There are cultural benefits, the inspiration that Mark mentioned, and there are also tangible industry benefits. And in the remaining 3 minutes of my presentation, I would like to focus a little bit on these industry benefits. So how and to what extent concretely the industry beyond patents can benefit from big science project. if we look at CERN, we see that the development of CERN to build the accelerator that currently exists involved a large number of firms. 4,200 firms have contributed the pieces that form the machine that you have seen in Mark's picture. And they involve 47 countries. So the impacts of the development of an equipment like the one that CERN is currently using are not limited to the local area where the accelerator is located. They unfold themselves throughout countries and in multiple locations through the demand for the different pieces of equipment that form this big machine. And what we did with Gabriele Piazza, who is sitting over there in one of the projects that we have conducted at the LSE in collaboration with CERN, is to track down these impacts, trying to look at how firms that have supplied CERN, that have supplied some equipments that are uniquely specific to large research infrastructure, so that have no other practical application, can generate impacts on the ground. And what we have been able to do is to measure the number of jobs generated by these procurement exercises. When large research infrastructure demand the pieces, these equipments are unique to a research infrastructure, cannot be used for anything else, so that you can really disentangle the impact of producing something that is exclusively used for science. And you can track down the jobs generated by this procurement. And what we could see is that, of course, like the companies that have been producing these equipments have expanded their employment. So there is like a positive impact on the firms that directly produce the equipments. However, for each job that was created by the direct supplier, 15 additional jobs were created in the local economy through input-output linkages connected with the supplier. Okay, so it's a pretty significant number that shows like a visible impact in terms of job creation, and these are not necessarily like scientists or high-level jobs. These are jobs linked with the manufacturing of the particular equipments that go into the generation of the large research infrastructure. So to conclude, like how can we make the ability to capture these benefits more and more visible? We need to understand more. We need to track down. We need our own like experiments, so to say, to follow not electrons in this case, but impact. And we need to be able to follow the money in order to maximize benefits, understand what works in practice in order to emphasize and boost these impacts, but also in order to enhance the political legitimacy of this investment vis-à-vis alternative uses of public resources. To be able to do this, we need to embed the evaluation into the project. So the project itself needs to have an evaluation component. And we also need to include an experimental component in the project itself in order to be able to try and test different possible arrangements that can lead to different types of impacts and outcomes. This is just some reflections on how we can make like this story even clearer and stronger when creating an argument beyond science to support the benefits of investments in big science. So we'll conclude with some questions for Mark based on these ideas. And like the first question that comes to my mind, looking at this presentation and looking at the current also geopolitical landscape, in how and to what extent CERN can work as a champion to support funding for big science and curiosity-driven research beyond CERN itself, but act as a multiplier, as an anchor to make the case for this coordinated investment in the EU and beyond the EU. To what extent should the scientific community, ultimately that's the purpose of this meeting, not really care? So us as social scientists, like experts of innovation, public policy, et cetera, we do care about innovation. But how and to what extent should like the wider scientific community care about the socio-economic impacts of big science vis-à-vis being purely driven by the academic and the scientific returns from these investments? And finally, like, what are the lessons that can be learned from CERN in terms of international cooperation? So how to make it work? What is it, in your view, like the magic, the boson that can keep the different funders together and achieve the objectives of these large scientific endeavors? Thank you very much, Mark. I look forward to your answers.
So what I'd like to do, Mark, is give you a chance to just, if you want to say a few words about the comments, and then, though, we'll turn to questions. And when we get to questions from the audience, just raise your hand. Someone will bring you a mic. Say just who you are, where you're from, very quickly. One quick question, so we can get a bunch in, and we'll go. Okay.
Yeah, I'll keep it short to give people a chance to answer questions. I think on the last one, why has CERN worked well? The way CERN was set up, it was a post-war project to bring Europe together. There were obviously concerns within Europe about cohesion around nuclear science, and a number of visionary scientists really started talking about how Europe should collaborate together in this strategically important area, but solely for peace. So in the CERN convention, it is science for peace, non-military applications, and that enabled CERN to be set up as an international treaty organisation. So international treaties are very difficult to establish, but when you do, it gives them a lot of stability. And really that I think has been part of it, setting up the boring bit, the governance of CERN in a way that it is very well defined, very clear mission. The other thing I think that's made CERN work, when I visit ambassadors in the Geneva region, I think CERN is their kind of almost their favourite. It's international collaboration, it's diplomacy, but it's science diplomacy, and it's kind of safe. It's a very, it's a really nice way to collaborate in a genuinely positive spirit. Whereas some of the other areas, I suspect the diplomatic community work on, it's quite a lot more challenging than that. And it is all driven by that common scientific goal, that common mission that I think everybody buys into. And I will come back to my comment earlier. It's not just about the science, it's the cultural value of what we're doing. And I think that's really important. Maybe also another one I wanted to touch on. There's so many things I could pick up on, and maybe we'll throw it open to the audience.
Okay, so
specific.
where are my microphones, by the way? So you guys should be out and about, and well, since we're here, let's start right down here.
Hello, Pardi Martina. I'm a postdoctoral researcher at the Inequalities Institute. First, thank you so much. I really enjoyed the presentation. I wanted to ask, you all hinted at it already, but let me ask it directly again. So every investment has also opportunity costs. So how do you respond to opponents that basically say that big pot of money that you invest into particle physics, why don't you invest it into climate change, into AI, into public health care and poverty? Asking that again.
It's a good question. Firstly, I think we need to do better at actually really demonstrating directly what the long-term economic impact of investing in big science is, and in fact, touches on your studies and actually really nail that down much more clearly than we have in the past. I mean, we have case studies. That's very clear. There is evidence there that the impact is very, very, very high, but we need to really refine those arguments. The other thing I would say about places like CERN, there is one in the world. Now, if I'm a financial investor and I'm going to look at investing my money, I don't have very much money, but if I had lots of money, I would invest in a portfolio. I would put a few big bets in really high-performing, high-impact scientific areas, and not look at it as I almost spread my types of investments out. So my investment portfolio has these big bets, brilliant science that could have massive impact downstream. So that's the way I would look at it. I think it's almost quite a dangerous argument, this opportunity cost argument, because I think that can drive you down to the lowest common denominator.
I do. I can't resist. I mean, if somebody had made that argument successfully after World War II, we would have so much less to address exactly the problems that you're talking about. So it's kind of, I think, answers itself almost in that way.
Can I just come in on that from a sort of a government point of view? Because Of course, one of the things that we do as chief scientific advisors is have to absolutely advise on that question as to the balance between investment in research and development compared to investment in delivery of school funding or education funding or things like this. A few years ago, there was a very influential piece of work that identified that it was of value to spend around 2.5% of gross domestic product on research and development. Now, the really important thing about that figure was that not all of it comes from government funding. In fact, only about a third of it would come from government funding, because we know that government funding can leverage that industry investment as well. Now, there was lots of thought and discussion that came up with that 2.5% figure. And if you look at industries, some industries will spend more than their annual budget than that on R&D. Others, as you showed in your analysis, are decreasing the amount that they spend. One of the things that's really interesting about being a chief scientific advisor is I advise. And we live in a democracy and politicians decide. And so feeding into that discussion is absolutely what we need to do. And it's tough because there isn't enough money to do all the things we'd want to do. And so that's where that sort of balance of coming up with the questions that are most important from society's point of view today, but also having a long-term view on the future is really, really important.
Over here. Well, okay, that's good too.
Hi, my name is Stephanie. The question I want to ask is how existential this problem of people, and by people I mean heads of states, not being able to work together is for the future of CERN. So you have America and problems in Europe as well. What happens if a bunch of Trump-like characters come into office?
Yeah, I think you're asking a question with no easy answer there. But again, I would come back to this sense that I think across European states, I'll start with the European states, CERN is seen as something quite remarkable and quite precious. And back in October, we had the 70th birthday party for CERN. It was a celebration. I think there were about 10 heads of states there, all backing CERN very positively, and across multiple regions of Europe and very different political backgrounds. So I think again there's this sense that there's something really good here, something really good for Europe, and that helps people to come together. In the future, of course, the US are actually a big contributor to CERN. They're not a direct member. I'm optimistic we'll find a way through that discussion. Again, it's around this is a good thing. It's mutually valuable for Europe to host this one place in the world, and for the US to be part of it. So we'll see how that one plays out. As I say, I'm definitely an optimist around just because there's something special, and I think everybody wants to keep that special thing.
Let's take a question from online.
We have a question from Diva Shah, who's an LSE alumni. They say, how do we involve the global south in STEM and socio-economic impact of big science?
It's a lovely question. Where do I want to go? So I can give you a couple of examples actually from when I was executive chair of STFC. So there's a big science project that I nearly put in this presentation, but I didn't because I just didn't have time. And that's the Square Kilometre Array Observatory. It's like the CERN for radio astronomy. There are 2 telescope arrays, one in Australia, one in South Africa. And what we, and I think the UK has actually been pretty good at doing, is trying to use that underpinning infrastructure that's being built in South Africa as a gateway to improving STEM skills and STEM engagement across sub-Saharan Africa. So it's not easy, but there are ways you can do this, and having these big infrastructures in those regions makes a huge difference. I think that really is the key. And the idea that Africa will come, scientists do come to CERN, But that's not going to make the big difference. It's going to be having something like the square kilometre array in Africa, so there's a sense of ownership across the continent. So really good question. Lots of desire to increase the engagement of Global South in infrastructures. That's just one example. I could speak a lot about this, but probably shouldn't.
Yeah, Mark, if I may, like also considering the supply chain that goes into CERN and how into oil in large research infrastructure, like the map of suppliers that we looked into, and we have seen it's not only like the member states, but there is a wider participation of firms located in multiple countries. So we can think about, and this is an area of like ongoing research, understanding what type of public policies can be used in order to widen participation, because these applies to the Global South, but also when thinking about support by current members want to see benefits spreading beyond their core regions, beyond the usual suspects in terms of the most economically dynamic regions within the member states and within the European Union. So the story and the public policies in terms of thinking about how we can spread the benefits beyond the usual suspects within countries and across countries is an area where social scientists can maybe offer like an helping hand in terms of seeing what type of policies have worked in other cases in order to spread these benefits and maximize the developmental returns in the north and in the south of the world.
So the way in the back, the guy with his young man with his hand up high.
I'm Florian Sibo, Masters in Environmental Economics and Climate Change, and I'm from Switzerland. Quick question on what the energy mix of CERN is, and with the energy transition happening, is solar and wind reliable enough to get to 99.999% of light speed?
Not 99.9999991. I mean, CERN's largest supplier of power is France, and it's from French nuclear power stations. So in that sense, it's not carbon intensive. There is also a move to secure long-term power. They're called power purchase agreements from countries like Spain, which would be solar. So the whole area of environmental sustainability, reducing carbon footprint in the future is a really, really hot topic, and it's one we're working on. But that just gives you a sense what the current energy balance is. And of course, that nuclear argument isn't necessarily a very good one, because actually what you should be doing is looking at the whole of the grid across Europe rather than picking out your favourite bit of it. But it's there are initiatives, particularly to directly source solar power as well. So a good question. Very, very high on the agenda for the future, that future project I was talking about.
And it's a topic that's really coming through in a number of different aspects of science. The obvious one is the very large compute facilities that are underpinning much of the artificial intelligence discovery we're seeing. The Royal Academy of Engineering is looking into that because it is an area which is really needing to have the best understanding of that balance between the opportunity and the discovery we can get from these new scientific approaches, yet the energy demand that they are creating.
The woman in the blue, all the way in the back, also. Then we'll come more forward.
Thank you. Hi, I'm Varsha, and I'm a health economist. And so my question to you is regarding the Hadron therapy. So UK doesn't have one right now, and it relies a lot on immunotherapy drugs, which are not as medically effective and are high in cost. And Hadron therapy is obviously very medically effective, and it comes mainly for like the most important cancers like brain, spinal. Yeah. And I was hoping to ask if there are any advances in that, or if there is any news of creating one in the UK to improve treatments.
We do. I mean, they're not there. I mean, the UK was quite slow to adopt Hadron therapy. So this is basically using protons rather than X-rays. And the advantage of X-rays basically just go straight through you. So they do lots of damage to surrounding tissue. So you have to blast the tumour from all sorts of different angles, and you do a lot of damage everywhere. Protons stop, and you can basically, if you get the energy right, they stop in the tumour and deposit most of their energy in the tumour. The UK now has 2 Hadron therapy facilities. We're still probably lagging behind countries like France. and they are primarily used to treat some of the very, very hard to treat cancers, or to treat young patients where that secondary damage is particularly concerning. So it's not as bad as it was a few years ago, but again, we could do more, and it really is. It's a very effective top-end treatment. There's a lot of research going on, which CERN is backing, about different types of hadron therapy, different types of radiotherapy, things called flash therapy, really exciting, where it seems that if you basically really blast really very, very high doses of radiation, cancer cells don't like it, but normal cells somehow don't seem to be so damaged by it. I mean, it's research, but it's a very important area.
Take another question online.
A question from Jose Antonio Belso, who's another geography alumnus. It's widely understood that CERN is a hub for high-tech research and development. How has CERN contributed to the formation of an innovation cluster in the Geneva region? And what lessons can other regions learn from this situation?
Oh, that's a great question, and I can give you two perspectives. So, previously, as executive chair of STFC, we ran the Harwell campus. Great example of innovation. You gave the numbers: 7,000 jobs, 250 high-tech companies, all in the local region. Lots of inward investment. Works brilliantly, and when it was active, we knew how to do it. We knew how to manage it. Now, the challenge with CERN is an international organisation. It's there to benefit the member states who pay for CERN. We could do something similar and create an innovation cluster around CERN. That would primarily benefit Switzerland and France. So then it creates disparities in benefits between the different countries. And that's why that particular type of intervention has not been pursued. There are other ways of doing it, like the European Space Agency has its business incubation centres, its BICs, which are then located in the different countries. For various reasons, I don't think that would actually work for the type of science CERN does. But it's a really good question. But it's that local stickiness of the innovation that's a positive thing when you do it nationally, but a challenge when you do it in an international organisation.
That's let's go over here.
Hi, I'm Devin. I'm a maths and physics student at Imperial Maths School. So this touches more on the physics side, but you mentioned how the experimental physics at CERN can lead to benefits. Do you see how these results could also produce advancements in theoretical physics, such as a potential relationship between the Higgs boson and the Higgs branch in supersymmetric theories?
I mean, the answer is kind of yes.
Any answer will work. No one else.
Yeah. I think what I would want to say is that you can't have experiment without theory, and you can't have theory without experiment. So advancements progress hand in hand. So sometimes there might be a big theoretical breakthrough that will then drive changes in experiment. Other times you might make experimental discoveries, completely unexpected discoveries that then change the whole theoretical paradigm. So I think it's very hard to predict how that will work out, but it's absolutely clear. I mean, CERN has a theory department, it has an experiment department, but the theoretical community is also absolutely essential to interpreting the data that we have in any way. So without really high-level theoretical input, you can't interpret data. And what we do see in theory and mathematics more and more is as it becomes more and more advanced, you start to see these areas of mathematics or theory that somehow can then be applied to other disciplines, other very advanced theoretical disciplines. And that happens a lot, and there's a very active area of research. I think the main message, though, theory, experiment, hand in hand, perfect harmony, and something like that anyway.
So let's go to the woman right here in the middle, then I will get to it, I promise. In the green jacket, I was thinking. But we can do both.
Hi, I'm Vandana and I'm a health policy student at LSE. My question is specifically about how Brexit impacted the work in CERN. And an additional question on top of that is, what political protective measures is CERN taking to preserve the growth of science in fractious political conditions in the European Union?
Oh, well, these are two difficult questions. So CERN is an international organisation, so it is to some extent independent of national boundaries. It is an international organisation, so that is a benefit. But of course, the UK scientists who were working or visiting CERN, or potentially living in France, have found it more difficult. Now, slowly, I think things are getting a little bit better. It's not, but it's not helped. Let's put it like that. The second question. I have to say, I think I'm always amazed talking to this. There's a big diplomatic community in Geneva. That general sense of coming together around CERN. Even I won't give examples of countries, but countries that are actually quite diametrically opposed on many issues within Europe. They're not when it comes to CERN. And I say I think this is a real benefit, that it gets people around a table, speaking with a common goal, common desire for success, and hopefully that then percolates through more widely. I'm not sure that's a very good answer, but it just gives you a sense of what it's like really on the ground.
What I'd like to do, because we're getting near the end, we'll take two questions, yours, then pass the microphone to him, and then answer, and then maybe if you guys want to do a little wrap-up comment.
Hi, is this working? Yeah. First, thank you, Professor Thompson, both for your talk, also your excellent textbook, which has helped me through several exams and a thesis. So my name's Alexia. I'm a current particle physics PhD student, and I was also a secondary school teacher teaching physical engineering. So I spent a very long time in physics education myself, and also delivering physics education. And one of the reasons when I saw this talk I wanted to attend it is because there really seems to be a lack of awareness of socio-economic impact, especially in these big science subjects like particle physics. It was at no point during my undergraduate, my master's, or my PhD. But basically, where do you think we should be focusing on increasing engagement of this within physics education and within education and schooling in general? Because I know this is also something that Professor Sharples mentioned.
Yeah, I would tend to agree with you. I mean, these are areas where I think we could and should do better. Both these areas. I think the desire to really demonstrate the wider benefits, the wider impact. I think that's coming quite sharply into focus now, and actually engagement with the social sciences is a huge benefit because, as a particle physicist, it's not something I'm trained to do. And I think there's a real impetus given to that now because we are talking about the next big project at CERN. And we are going to be asked those difficult questions. So I think the wider community, the wider scientific community is realising that we really have to tackle this now. And I think that also feeds into the second bit of the question, which is around engaging with the public, using big science to really inspire. And we're not talking about inspiring 18-year-olds. We're talking about inspiring primary school children because that's where part of the pipeline breaks. And again, I think this is part of this case for this next big project that we need to demonstrate that it's going to have that impact on actually attracting people into science and engineering subjects. And I think I think we can do better, and that's certainly something I'm personally committed to doing. Have said that over the last few years, that we just need to sharpen our arguments and get those arguments out there, not in a scientific way, which particle physicists tend to complicate. I think recognise things are complicated, but then make the arguments quite complicated. We need to sharpen those arguments down, really distill them down into the core.
And it comes back to that multidisciplinary discussion. So I was talking today to the Economic and Social Research Council, who fund an organisation called ScienceWise, who both conduct public communication activity, but also do something called deliberative research, which takes quite difficult engineering and science concepts out into the public domain, we can sometimes be at risk of being a little bit almost patronising and protective of the complexity of science and engineering. Actually, through communicating in an accessible way quite complex concepts, such as we saw today, we can stimulate really, really important discussions amongst the public. And so expert organisations like ScienceWise are a really important part of the ecosystem. The interesting thing about a lot of these research is they're not big, shiny facilities. So making sure that we're funding the expertise in public communication and public dialogue alongside the big, shiny facilities that are so important for this scientific discovery is really, really important.
So last question, and then I'll ask each of you to...
My name is Konstantin, and I study political economy of Europe at LSE. Mr. Thompson, do you think scientific progress may be slowing down? Will we eventually reach a point of close to no new discoveries? What would be the consequences of that?
Depends what you mean, scientific progress. I think I would actually argue in many fields scientific progress is perhaps accelerating, and it's accelerating because we're giving subjects, I'll take structural biology as a favourite of mine. We're giving the structural biologists the tools to do brilliant biology, so you can actually now start to design proteins, really design proteins that will solve, will cure specific diseases. In fundamental science, I gave a talk a couple of months ago where I tried to go through all of the big discoveries of the last 100 years. And we've had a few recently. Gravitational waves, massive discovery, absolutely massive discovery. The Higgs boson, absolutely massive discovery. Neutrino masses, absolutely massive discovery, bad pun. But the frequency is roughly every 10 years you get one of these really major fundamental breakthroughs in big science, particle physics or cosmology. So let's wait. And you don't see that tailing off. And you don't know what's going to come next, because we are doing, the other thing I'd argue is we're doing all of the right experiments. We're doing all of the right, we're pushing at the energy frontier with the LHC and the high Lumi LHC. We're doing really big neutrino experiments. They're very exciting. Searching for dark matter. Don't know where the next one's going to be, but it's these big things. They don't come on every, it's not every year that you get one of these absolutely groundbreaking discoveries. And I don't see that slowing down.
So let's just final comments from, and then I'll give the last word to you, Mark. So Ricardo, do you want to go?
Well, yeah, I mean, I'm really amazed by the conversation we had that shows like how the social sciences can really interact with the hard sciences and come together and offer something that combines like scientific breakthroughs with the social sciences, public policies, and how we can make all these like work for society in the best possible manner. So I just would like to share the reflection on how interesting this is, and I really hope this would be just the beginning of a continued conversation with CERN and other research infrastructure at the LSE.
So thank you for inviting me to participate in what I think has been a great discussion and brilliant questions from the audience as well. I think there are three things I'm going to take away. First of all, the funding of big science facilities such as the ones we've heard about today, I believe is absolutely fundamental to solving some of the critical issues that are facing society worldwide. And so making sure that we rehearse that argument and understand that argument is really important. I think the second thing is that these facilities do provide an opportunity for national and collaborative leadership, and they create talented communities. We need so much scientific and engineering discovery to help us solve these problems, and people will be absolutely at the heart of that. And then the final thing is, it's really fun, it's really exciting, and it's really energizing. And one of the things that I sort of am not at all embarrassed about is making this exciting and fun and energetic. Excuse the pun again. And so I think that actually we shouldn't shy away from the excitement and the joy and the awe of science, because actually through that motivation we can end up with some of the amazing discoveries that we heard about from Mark today.
Final.
Right, I think I've spoken enough, to be honest. I just really want to thank everybody. It's been a huge pleasure coming here, actually. I think it's a different kind of discussion than the kind of discussions I often have. Very rich, really interesting. So actually, I just want to thank everybody for their contributions and wonderful questions. I think for me, it's been a brilliant evening. Really, really, really enjoyable and exciting.
Well, I think the thank yous all go the other direction. So on behalf of the audience, I think you'll all join me. Thank you so much. And